Hello everyone, welcome to Artistic Atom channel. I'm Fatima and today we will be discussing mass spectrometry. This is going to be the part 1 of this session. In this session we will be discussing mass spectrometry in detail along with some of the exam oriented questions which will help you in understanding what type of questions may be asked on this particular topic. Also I'll be sharing a smart trick for the fragmentation with which you will be able to determine the exact fragment of the given molecule. Okay, so let's get started. Now, before going ahead and understanding the different ways of fragmenting a molecule, let us first understand instrumentation of mass spectrometry so that we are clear on what principles mass spectrometer works. So this is how actually a mass spectrometer looks like. It consists of different parts where they have different functions. Okay, so firstly what do we do is we inject the sample. So this is the point through which we inject the sample. As soon as sample enters the mass spectrometer, there is a heater or a hot plate which converts this sample into its gaseous state. This means after sample injection we carry out the process of vaporization. Once they get vaporized, here we have electron beam. So these high energy electrons, what do? They actually knock off the electron which is loosely bonded in that particular gaseous substance. So as soon as they knock off that one electron from the gaseous substance, that process is called as the ionization. So after ionization, these ions, or specifically we call them as what, radical cations. Okay, because there is just one electron that they have lost. Other one is still there with them, so they have an electron and also a positive charge, hence we call it as what, radical cation. Now that radical cation undergo fragmentation. So once we have got that radical cation, it breaks into different fragments based on their stability, which we will discuss in further slides. And after that it undergo acceleration. So we use two electrical plates in order to accelerate these charged ions. So as soon as they get accelerated, they comes in contact with the magnetic field. Once they comes in contact with the magnetic field, they get deflected. Okay, we will also discuss about deflection in detail in further slide. So once they get deflected, they get separated based on their masses. As soon as they get separated based on their masses, we have a detector which detects them, and finally we get a mass spectrum for the given substance. Okay, so this is how actually mass spectrometer works. Now here I have put the notes for you so that you can go through these functions of different parts of the spectrometer in detail and also clear your queries if you have. Now let us discuss deflection in detail. So when I use this term deflection, what do you mean by it? So deflection is nothing but when the magnetic field pulls a radical cation sideways. So suppose if it is pulling it easily, this means the radical cation is getting bent easily and deflected easily. Hence we will say that the deflection is more. And suppose if the radical cation is very heavy and it is very difficult for the magnetic field to pull it sideways, hence instead of getting bent it will go almost in a straight way and gets into the detector. Hence we will say that the deflection of that particular radical cation is very less. Okay, so remember this, that the as we have the higher mass of the ion, radical cation, it bends less and hence they will have the larger radius of curvature, as you can see over here. Because we have higher mass of that particular radical cation, it took a longer path and has the longer radius of deflection, and hence we will say that they will get bent less. This means they have less deflection. And in case of lower mass, what happens, they will get bent to more extent. Because they have less mass, it is easier for the magnetic field to pull them sideways, and hence they will have the smaller radius of curvature. Now, the next question is, why isn't mass spectrometry called spectroscopy? Like we call IR and NMR, like we call it as what, IR spectroscopy, NMR spectroscopy. Why we call mass as what? Mass spectroscopy. Instead, we call it as what? Mass spectrometry. What's the reason? Well, the reason is this, that in case of mass spectrometry, we do not use any electromagnetic radiation. So only the spectroscopy techniques where we use radiations, we call them as what? Electron spectroscopy techniques. Okay. And suppose if there is no involvement of the spectroscopy techniques, we call them as what? Spectrometry. Instead of using radiations, what do we use? We actually ionize that particular substance, and then we make it undergo fragmentation, and as soon as it undergo fragmentation, based on their mass to charge ratio, it get separated, and finally using detector we detect the different fragments, and at the end we'll be able to make out what was the exact structure of the substance which we used at the beginning. So this is what do we do in mass spectrometry. Now there is one more thing that you should remember, that when we take mass spectrum of any substance, there are two kind of substance that you may come across while taking the spectrum. First one is the organic compound, and second one is the element. So when we talk about organic compound, in case of organic compound, the mass spectrum consists of different lines, and each line represents the different fragments of that particular compound. Okay. But in case of elements, what happen? Each line represents different isotopes instead of their fragments. So we get the information about their isotopes. So in conclusion, we can say that whenever we are having organic compound, we will look for the different fragments that it is going to form, and those fragments will appear in the mass spectrum. But in case of an element, what happens? The element will show the mass spectrum based on the different isotopic peaks. Now here are the different uses of mass spectrometry. So firstly, as we have discussed, that we use it in order to determine the molecular mass of the substance. Once we know the molecular mass, we'll be able to easily anticipate the molecular formula of that particular substance. And once we are aware of the molecular formula, we can also determine the purity of that particular sample. Okay, so I'm just going in the flow of these points. Now, the next one is we can also determine the isotopic composition. So, once we are aware of the isotopic composition, we know their relative abundance of these particular ions. Okay. And also, when we are determining the molecular mass, so firstly we determine their fragments, and based on these fragments, we predict their molecular formula, and finally we get the molecular mass. Okay. So, these are the different uses of mass spectrometry. You have questions based on this. So let us move ahead and understand different questions that may be asked on this particular introductory concept that we have discussed till now. Now the question one is, which one of the following statement is correct about the spectroscopic technique for organic molecules? So here we have different spectroscopic techniques. We have to make out which one is the correct one. So the first option is, information about bond vibration can be deduced from mass spectrometry. So well, in case of mass spectrometry, what do we use? We use radical cations, and we determine molecular mass. We do not determine the bond vibration. So this statement is incorrect. Now the next one is, the value of carbon hydrogen bond length can be determined from 1H NMR spectroscopy. So well, whenever we talk about the bond lengths, we use X-ray crystallography, because this is the technique that gives the exact length of these bonds. Okay. Now this means this option B is also incorrect. Now the next question is, the number of hydrogen atoms can be determined from infrared spectroscopy. So well, we use infrared spectroscopy in order to determine the functional groups, not the number of hydrogen atoms. Okay. Instead of, we use combustion analysis to determine the number of carbon, hydrogen, and sometimes oxygen atoms. So this means this statement C is also incorrect. Now the last statement is, information about molecular structure can be found from mass spectrometry, which is absolutely correct. Okay, this has to be spectrometry, not spectroscopy. So please do the correction. Now the next question is, which of the following of the spectroscopic identification will involve bond fission in organic molecule? So the here they are asking which of the technique will involve the bond fission. Bond fission means breaking. Okay, so here we have option A. So in option A we have nuclear magnetic spectroscopy. So in case of NMR we do not break a particular bond. Instead we just check for their resonance. Okay, in case of infrared also we look for the vibrations. In case of mass spectrometry, what do? We break or fragment the organic molecule into smaller pieces. The process is called as what? Fragmentation. And fragmentation is nothing but breaking of a covalent bond, which is nothing but fission. And once we break that particular organic compound, it gets broken down into its radical and radical cation. Okay, this is what actually happens in mass spectrometry. This means option C is the correct option for this particular question, because this is the only technique which involves bond fission. Now, the next and the most important topic is ionization. So, from this slide onwards, we are completely understanding the ways by which we can easily determine or anticipate the fragment of any of the given organic compound. So, the first step in fragmentation is the ionization. So, firstly, what do? We take our organic substance, we bombard high energy electrons, and these electrons will knock off the loosely bonded electron from that particular organic compound, and they get convert it into what? Radical cation. Okay, so since this is the first cation that is formed out of our molecule, we call it as what? Molecular radical cation. Okay, and this is how actually it looks like. It has a positive charge and one unpaired electron. Now always remember, this is the most important thing to remember, that is the order of electron removal, that is from where you will remove that electron, because whatever organic compound you are provided with, you may have covalent bond, you may have a pi bond, you may have lone pair of electrons, so which one to remove? So always remember this order. If you have non-bonding electron, non-bonding electrons are nothing but the lone pair of electrons, so you will remove one electron from that lone pair. Okay, if you have pi bond, only pi bond or pi bond and covalent bond, then you will remove one electron from pi bond. And suppose if you have only sigma bonds, okay, so in case of only sigma bonds, you will first try to break carbon carbon bond, and then you will break what? Carbon hydrogen bond. So these are the priority orders that you will follow while carrying out ionization of any of the organic compound. Don't worry, we will discuss it in detail taking few examples. Now, once we are done with ionization, the next step is to carry out the fragmentation. When we talk about fragmentation, there are questions based on alkanes, alkenes, and different organic compounds involving heteroatoms. Okay, so I have categorized this whole method of fragmentation into two categories. First is based on alkanes. If you have alkanes, how you are going to fragment them, and secondly, if you have alkenes or any heteroatom containing compound, how you are going to fragment it. So in case of alkanes, we may have aliphatic, that means completely straight chain, and we have branched chain. Okay, so this means if we have completely branch chain and completely straight chain, but they are purely alkanes, there is no double bond, triple bond or any heteroatom, then you're going to follow this method. And while carrying out the fragmentation, the most important thing that you will remember is the stability of the carbocation. So based on the stability of the carbocation, you are going to carry out the fragmentation. Now next is the fragmentation of alkenes or heteroatoms. So when we talk about alkenes and heteroatoms, here we have pi bonds and also we have non-bonding electrons associated with these heteroatoms. So if you have alkenes, then you are going to make sure that your double bond should undergo ionization. This means that double bond will get converted into what? A radical cation. And if you have any heteroatom present, so they have lone pair, which are nothing but the non-bonding electrons. Hence, I will ionize the lone pair of these heteroatoms. So remember these points, okay? And lastly, what do we do? Once we have ionized them, we will carry out the fragmentation. And always remember, in case of alkenes and heteroatom, we always follow alpha fission. Okay, I will explain this in detail in further slides, so don't worry. So this is the conclusion. That is, whenever you have fragmentation, check if it is an alkane, you're going to follow the stability of the carbocation in order to carry out the fragmentation. But when you have alkenes or any heteroatom present, then you will look for pi bond or the lone pair, depending upon which one is present, and then you will do the respective ionization. And after that ionization, what you will do? You will do the fragmentation following alpha fission. Okay. Now, when we talk about ionization, ionization always results in formation of what? Molecular ion. Molecular ion will always have the highest MZ value. Okay. So if you have the molecular highest MZ value in the spectrum, you will say that this is my molecular ion peak. Okay. Now, as soon as we have formed our molecular ion or radical cation, it will undergo fragmentation. Now, the first step in fragmentation, or the first fragment that you get, is called as the primary fragment. Always remember, primary fragment is the most stable fragment in the whole fragmentation process. Whatever is the fragment is going to form, this primary fragment is going to be the most stable one. Hence, we call it as what? Base peak. Now, when we carry out the fragmentation, always remember, you are going to fragment your molecular ion in a way that it should result in the most stable carbocation. Okay, and you will call that particular radical cation as what? Your primary fragment. Once you have got your primary fragment, you are going to carry out the secondary fragmentation. Always remember, if after the formation of the primary fragment, that primary fragment undergo further fragmentation, because we have a lot of energy present with these molecules, so it again undergo fragmentation, only the primary fragment. Okay, and it results in the formation of another fragment, to which we call it as what? Secondary fragment. Okay, so this is the step 2. Then after secondary fragment, whatever is the most stable secondary fragment, that will again undergo further fragmentation, and we call them as what? Subsequent fragments. Okay, now there is one more point that you should remember. Till what point you're going to continue this fragmentation process? Well, fragmentation carries out till the molecule have too low energy to break down further, or it is too small that it cannot be broken down further. Till that point it is going to break. So the next question is, are you going to do the fragmentation till that point in exam? No. What you're going to do, you're going to write the molecular ion, then you will show the primary fragment, then you will show the secondary fragment. That's it. Because it is enough to predict any of the molecule from the mass spectrum. Okay. Now, let us take an example. So here I have a branched alkane. Okay. So this is a 2-methyl butane. Now in this branched alkane, firstly I will do ionization. Okay. So once I do the ionization, I have few options that which bond should I ionize. Since all of them are sigma bonds, you can ionize any of the bond. Okay. So I have put my radical cation over here. So this species which is formed is called as radical cation, and I will also call it as what? Molecular ion. And it will have the M by Z value as 72. And this is going to be the highest M by Z value. Okay, and I will call it as what? Molecular ion peak. The peak it is going to give in the mass spectrum. Then after this, always remember, since we have all sigma bonds, so you can break any of the sigma bond to form the radical cation. Okay, this is what I told you earlier. Now, once we are done with the formation of the radical cation, in order to explain you in a better way from where the bond will break, I have marked this carbon as what? Carbon 2, carbon 3, carbon 4, and so on. Okay. So now what I will do, the first option is that this carbon 1 and carbon 2 bond will break. So if I break carbon 1 and carbon 2 bond, I have I will have one radical cation, one radical, and another will be my radical cation. So based on the stability, because see, you what you will say that ma'am, you might you have another option that you can put positive over here and radical over here. So well, as I told you, you're going to select the fragment where you will have the more stable carbocation. So if I check in between methyl carbocation and this carbocation, I can clearly see that this one is the secondary one and this is going to give me the primary one. So instead of giving plus charge to CH3, I will give plus charge to what? This particular species as my carbocation. Okay. So now this will have M by Z values as what? 57. I can also write this particular radical cation species like this. Okay. C4H9 plus, and there has to be one radical. Okay. So this is how I have got the first fragment. Now there is another possibility that instead of breaking this bond, I can break this bond. So I have, after breaking this carbon 2 and carbon 3 bond, this is what I am end up with. Okay. So I can see that here I have got the option of cation over here and this one as radical. I told you follow the stability of the most stable carbocation. Then only you will select the fragments. Okay. Which one will get the positive charge, which one will get the radical. Okay. Then nextly, the next option that we have is this one, that I can break carbon 3 and carbon 4 bond. So these, if I break this, then I will end up with this as my radical cation and this one as my radical. So these are the three options. Now the question is, which one should I select as my primary fragment? Should I break it this way in exam as my primary fragment, or should I break it in this way, or should I break it in this way? So, well, the simple clear-cut answer for this question is always follow the stability, okay, in case of alkanes. So, when we talk about stability, it is not just in case of alkane, but specifically since I'm discussing this, I suggest you to follow the stability of the carbocation, okay. So, as we see, here we have these two options, okay. So, if I follow, this is what the question you had. So answer could be this, that whenever we have these kind of cases, we will look for the highest stability of the carbocation. So we see that the third option that we had, there we were having primary carbocation and then we had secondary carbocation. In these cases, this means these two are more stable compared to the third one. This means I should go in either by this way or by this way. So which one should I just select after between these two? So well, you're going to select where the cation is more stable. So I can see that here it has more alkyl group or the carbon groups attached, which are strong electron donating group, and carbocation is the electron deficient group. So as it is electron deficient group, it needs more electrons so that it can stabilize itself. Hence, I can say that in this case, this carbocation is more stable than that of this one. Again, there is another way to explain the same thing. That is, if we have more number of hydrogen atoms present, especially the beta hydrogen atom, it will have more hyperconjugation. And as the hyperconjugation increases, the stability of that particular carbocation also increases. Okay. So we can also discuss the stability based on their beta hydrogen presence. So as you can see that in this case, I have 3 beta hydrogen. How you will determine the beta hydrogen? As you can see, this is my radical cation and the carbon next to the radical cation is called as the alpha carbon, and the carbon next to the alpha carbon is called as the beta carbon. So on beta carbon, I have 3 hydrogens. So these are 3 beta hydrogens. Whereas in this case, I just have alpha carbon, there is no beta carbon present. So this means there is zero beta hydrogen atoms. This means this one will have the higher hyperconjugation that of this one. Hence, this radical cation will be more stable than that of this radical cation. Okay. So this means I will go with this as my primary fragment. Now, after we have got this primary fragment, we will also call it as what? B speak. After doing this, we will carry out the further fragmentation of the primary fragment. Okay. So because in exam, they should always remember to determine the three peaks, that is the molecular ion peak, primary fragment peak, and nextly the secondary fragment peak. Okay, so we have got our primary fragment peak. Now let us determine the secondary fragment peak. So here is the organic compound that I have to break it further. Okay, so in this there are two options that by which I can break. Okay, so firstly I can break it this way or I can break it this way. So as I told you, follow the stability of the carbocation. I can see that if I break it this way, here I will get the radical and here I will get the carbocation. Okay, so here am getting the primary carbocation, and this I will call it as what, my secondary fragment. Now this fragment can be further broken down, and when we break this particular fragment radical cation further, we end up with this. So this will be called as what, my subsequent fragment. So this is how actually we follow the process of fragmentation. That is, whatever is the organic compound given, first form its molecular ion. Once you have formed this molecular ion, go for the fragmentation, where you will get your first fragment, to which you will call it as your primary fragment. It is also called as the base peak because it is the most stable radical cation formed in the whole fragmentation process. Then after you have got your primary fragment, you're going to fragment your primary fragment further into secondary fragment, and then if you want, you can stop there, or you can further divide your secondary fragment into the subsequent fragments. You are going to carry out this fragmentation process, if you want, till the point when the molecule cannot be further divided, or if the energy of that molecule is exhausted completely. Now let us understand the fragmentation process in case of alkenes. So here I have one propene. So the first step that I'm going to do is the ionization. So wherever is the double bond, I'm going to ionize that bond to form the radical cation. That means that electron is going to be knocked off by the high energetic electron bombarding. So after that, it will result in the formation of what, radical cation, and it is also called as what, molecular ion peak, and the MZ value is 42. And as we discussed that the radical cation formation will only occur at double bond. Why? Because order of electron removal was this. If we have non-bonding, then they will go first. If we have pi, they will go first. If we have sigma, then this is the option. Okay. So this is how we carry out the ionization. After we have we have done ionization, the next step in case of alkene is to determine the alpha carbon. Alpha carbon is nothing but the carbon next to the radical cation. So as we see that this radical cation is formed between these two carbon, so I can see that adjacent to this carbon there is no other carbon. So I will go and check for this carbon. So I can see that there is one more carbon over here. So I will call it as what, alpha carbon. Now after selecting the alpha carbon, you will look for, if I open the structure, this is how actually my alpha carbon looks like. Okay, after determining the alpha carbon, you will look for the alpha bonds. Alpha bonds are nothing but the direct bonds attached to the alpha carbon. So I can see that this is my alpha carbon and these are the four alpha bonds. Because in case of alkene, we carry out the fragmentation only at the alpha bonds. So I can see that here I have three hydrogen alpha bond and one carbon carbon alpha bond. So I have two options. Either I can break hydrogen alpha bond, or I can break carbon carbon alpha bond. So as you can see, if I break hydrogen alpha bond, so it is going to break this way, that I'm going to get hydrogen free radical and I'm going to get carbon free radical. Okay, so this is how I'm going to end up with my radical cation. Only after breaking down or carrying out the fission, in case of carbon carbon alpha bond, this is how I'm going to end up with my radical cation and a radical. So as you can see that here I have these two radical cations and these two radicals. So only the radical cations, the charged species, will be detected in the mass spectrometry. Then what will happen to these radicals? Well, these CH3 and hydrogen radicals, they will go in the vacuum, okay, and they get lost in the this mass spectrometry machine, okay. Now the MBZ value for this particular fragment is 41 and the MBZ value for this particular fragment is 27. So which one should we consider as our primary fragment? So as I told you, follow the stability. So when we discuss the stability, as you can see, this is my allyl cation, okay? And this one I will call it as what? Vinyl cation. So in case of allyl cation, there is always resonance that happens because we know the structure of allyl and we know how the resonance happens. This means allyl cation are always more stable than that of the vinyl cation. Hence, we will consider this as our primary fragment and I will call it as what? Primary fragment or the base peak. And always remember there is a note for you. In mass spectrometry, then what you will say that, ma'am, in mass spectrum, I should get the peak only for this. Then when I am able to see the peak for 27 also, but you told me that only primary fragments will appear in the mass spectrum because they are more stable. Well, no, it's not the case. All the possible fragments will appear in the mass spectrum, but only those which are more stable will be more intense. Okay, so this means their peak will be more tall than that of the other cations peak. Since they are very unstable, they will be formed in very small numbers, because the priority or the favorable step is this, because it will result in the formation of more stable radical cation. So let us revise the steps for the fragmentation in case of propene. Firstly, we will carry out the ionization, where we will ionize the double bond. After we have ionized the double bond, we will look for the alpha carbon. After we have determined the alpha carbon, we will look for the alpha hydrogen. And after we have determined the alpha bonds, then we will carry out what? Fragmentation. So we will fragment the all possible alpha bonds and we will look for the most stable radical cation. That will be our base peak. Okay, so once you have practiced it a lot, you will be pro at it and you can easily do this without pen and paper. Okay, now the next step is to carry out the secondary fragmentation. So this is the primary fragment that we have selected and this is our base peak. Now if I open this structure, I can see that this is how my structure looking like. I have removed this radical or this electron just to avoid the confusion, because it doesn't matter whether that electron is there or not in mass spectrometer, because we are not going to draw any stable structure, and they don't even ask it in exam to draw any stable structure of these fragments. Okay, we just wanted to determine what could be the possible molecular formula for that particular fragment, so that we'll be able to determine its respective peak in the mass spectrum. So this is how actually my primary fragment looks like. Now if I carry out the fragmentation, I know that it is going to happen at alpha carbon. So this is my alpha carbon and these are my alpha bonds. So these are two ways. I can either break one of these hydrogen bonds or I can break this carbon-carbon bond. So if I break this carbon bond, I'm going to end up with this species where I'll be having this M by Z value, that is 27. And if I break this one, okay, if I break this hydrogen, one of the hydrogen bond, this is how I'm going to end up with. So I can see that again this is allylic cation and this is vinylic cation, and as discussed, allylic cation will be more stable than that of vinylic cation. So this will be my subsequent peak. Okay, and you can even carry out the further fragmentation. Like this one is the most stable, so again you can take it, you can again remove one hydrogen and you can carry out the fragmentation and you will be able to see these M by Z values. So this is how actually we do the fragmentation. Once you are going to do the practice, you will be skilled at it and you will be easily able to crack the questions. Okay, Now let us check whatever we have determined theoretically whether it matches with the spectrum, because in exam at the end we are going to get a spectrum or somewhat questions based on those spectrums. So we should know whether the data that we have determined till now is reliable or not. So these are the three most important peaks that I have got. First one is the molecular peak at 42, second one is the base peak at 41, and secondary fragment at 40. So this is the mass spectrum of one protein. I will zoom it in so that you'll be able to see the values of these peaks properly. So as you can see here, I have got the highest or the most intense peak, which is as 41. And yes, it is absolutely correct because it is going to be our base peak. I can clearly see that I have my molecular ion peak at 42. Okay, and nextly I can also see that there is a secondary fragment at 40, which is over here. And now you will ask me, what are these different lines or the peaks that you will be able to see in the mass spectrum? Well, these peaks are the different fragments, other fragments than these which are formed, but since they are very unstable, their intensity will be less. Okay, and you will ask me that why this 27 is more than that of these peaks. Well, because in most of the steps, the most common fragment which was formed was 27. So the number of fragments that were formed for 27 were more. Hence, its intensity is quite more than that of these other peaks. So always remember, major peaks shows stable ions and minor peaks shows the molecules breaking further under high energy. So it is not always uh, that these peaks which are there, that is these 24, 25, these all peaks are stable. These all are unstable carbocations which are, or radical cations which are formed. Okay, since they are charged particles, they are getting detected in spectrum. Now, this is the questions which you may come across based on this fragmentation pattern. So the question is, which of the compounds shown below is likely to have a fragment at m by e 45 in its mass spectrum? So here I have these four options. So the simple method is to carry out the fragmentation. The one which will be having the m by z values equivalent to 45, that is going to show the fragment in the mass spectrum. So this is my option A. Okay, carboxylic acid. So I can see that this oxygen has two lone pair of electron. I'm going to carry out the ionization. So this is how actually I'm going to end up with my radical cation, and this is my alpha carbon. And I'm going to break the alpha bond. So I'm going to break this alpha bond, that is carbon carbon. You can check out the other bonds also, but you will be able to see that here you will end up with the most stable carbocation. So I'm ending up with this species. So this is the radical cation and this is the radical. So these radicals will not be detected in the mass spectrum, only the radical cation will be detected. And the m by z value for this radical cation is what? 45. Now let us check for the other options also, because it is clear that the answer for this question is this, because the m by z value for this particular radical cation is 45. But still let us check other options. So in option B, I have the possibility of this fragment. You can carry out in different steps so that it's clear to you. So once we carry out the fragmentation, I'm going to end up with this radical cation and this radical species. This radical will not be detected, only this radical cation will be detected, and the m by z value is 59. If I check for the option C, then this is what I'm going to end up with, and the m by z value is 31. Here also the radical is not going to get detected, and I can see that the m by z value is 31. Now again I'm going to check for the option D. Here I'm ending up with this radical cation and this radical. This radical will not be detected and the m by z value is 31. So I am very sure that the answer is going to be this for this particular question. So this is how you're going to solve these questions. Okay. Thank you for watching. Do like, share and subscribe to my channel Artistic Atom. If you have any queries, do mention it in the comment section. I'll be really happy to answer them. If you want me to teach any specific topic, you can mention that as well in the comment section. See you in the next session.